friends, I am Chandan. Today's topic is closed system work analysis, or you can say that non-flow work analysis or fixed mass system work analysis. So closed system is basically non-flow work analysis or fixed mass system analysis. Let's consider this is a piston cylinder arrangement. This is a piston cylinder arrangement here. So here this is the piston here, sorry, this is the cylinder, and this is the initial position of the piston. So this is the initial position of the piston, and inside this system, so this is our system. Here you can measure the properties, that is pressure, volume, temperature. This is the initial condition of pressure, initial property, that is pressure, volume, temperature. Now if you want to calculate, so this is the initial position, okay, this is the initial position, and if you transfer this piston from this position to position 2, then you have to do some work. Okay, so if you want to calculate the work W, if you want to calculate work W, W is equal to, we know that, F into D. F is the force and D is the distance. So F into D, that is the work done. Now we basically know that P equal to F by A. So from here you can say that F equal to P into A. So thus just put the value of F. So work done formula will be W equal to P into A into D. So A into D, area into distance, this is basically volume. So volume here, volume, this is basically A into D. Area into distance, this is volume. So this formula will goes to W equal to P into V. So here F is the force, D is the distance, P is the pressure, and A is the area. Now if you want to calculate this, if you want to calculate the small work done dW, that is equal to F into dx. Full total work done W equal to F into D, distance. But if you want to calculate the small work dW, that is equal to F into dx. Now dx, that is equal to, we know that F equal to P into A. So from here you can see that dW, that is equal to P into A into dx. If you want to calculate the total work, you have to integrate this work. So integration dW, that is equal to integration of 1 to 2 P dV. So 1 is the initial state and 2 is the final state. So basically this is the work done formula. This is the generalized formula of work done W equal to integration P dV for closed system or non-flow process. Non-flow process. Okay, so this is the generalized equation W equal to integration P dV. So this equation is applicable only when it is a closed system, it is a reversible process, and it work process boundary. So if these three conditions if satisfied, then you can apply this equation. Now suppose focus on this graph. Here this is the y-axis and this is the x-axis, and suppose this is any process. If this is any process, now if the area is drawn on x-axis, then it is known as integration y dx, and if area is done on x-axis, basically this is this area, that this area will be known as integration x dy. So in the above equation, you can say that W, that is equal to integration P dV. So from here if you see this graph, so P is the y-axis and V is on the x-axis. Now this is any process. Now what is the work done? So if you draw a line perpendicular to the volume axis, then this area is known as integration PdV. So basically the closed system work is area under the curve of PV diagram on volume axis. Okay, so this is the area. Closed system work means area under the curve of PV diagram on volume axis. Now if there is expansion work, suppose there is volume is increases. In the above case, suppose this is the piston cylinder arrangement and this is our initial condition. Now the area is increases, volume is increases when piston is going to section 2. So when the volume is increases, then there expansion work, you can say that this is the expansion work. So this is the expansion work, volume increases, so this will be positive work. And if there is a volume decrease, that means compression work, and this will be negative work. Okay, now for open system, if you want to calculate this open system work is that is equal to minus integration VdP. So if you draw, the P is on the y-axis and V is on the x-axis, this is any process, and if it is a open system, then area under the curve on pressure axis will give the work done. Okay, so this equation is applicable only when it is a steady flow reversible process, and it is applicable only for open system. Remember this formula is only applicable only for open system. So this is very, very important. Now let's understand work interaction in different process for non-flow or closed system. So let's try to understand what work is produced on a closed system. Suppose first understand constant volume process. That means it is also known as isochoric process or isometric process. So constant volume, that means volume is equal to constant. So volume is equal to constant, that means derivative dV of this volume, that will be 0, because we know that derivative of any constant, this will be 0. So dV, that is equal to 0. We know that the closed system work W equal to integration PdV. So here dV is 0. So that is why work done for constant volume process, this is 0. So this is very, very important for if you want to calculate this closed system volume work, then it always equal to 0. Now this is our PV diagram. So P is on the y-axis and V is on the x-axis. Now so here this perpendicular line, this vertical line indicates that this is a constant volume, because here the volume is equal to constant, and if the arrow is upside, that means there is a pressure is increases. So if the pressure is increases, suppose this is a system here, this is a system, and this is you apply some heat from here, and it is a control volume, that means it is a constant volume process. So here volume is equal to constant. When you apply some heat, that means inside this system the pressure is increases. So here it is a constant volume process. So first draw the horizontal line, and it is, if it is heat arrow is upside, then it is a heat addition process, because you can see that there is a pressure is increases. So there is a pressure, suppose this is 2 and this is 1, so P2, here this is P1, that means pressure is increases. And if the arrow is downside direction, that means it is a heat rejection process. So this is my handwritten notes which is available on the description link. You can download it. uh, just try to understand it. Not don't write anything and anything. Okay, just try to understand it. Now focus on the constant pressure process. Constant pressure process, it also known as isobaric process, or it is also known as isopistic process. Okay, so this is here pressure is equal to constant. So P equal to constant, we know that closed system work, that is equal to W equal to integration PdV. So PdV 1 to 2, that means state 1 to state 2. So this is equation is applicable only while closed system, reversible process and work crosses boundary. Now if you want to calculate, then W equal to P integration P into V2 minus V1, W equal to P into dV. So this is the work done for a constant pressure process. So this is basically applicable only when it is a closed system, reversible process and work crosses boundary. Now if I see that, so there is a pressure on y axis and volume is on x axis. Suppose this is any process, so if the arrow is in this direction, that is a heat addition process because volume is increases, and if the arrow is in opposite direction, that means this is a heat rejection process. Okay, now focus on the isothermal process. Isothermal means temperature that is equal to constant. If you want to calculate work done, what is the formula? W equal to integration PdV. So this formula is applicable closed system and reversible process and work process boundary. This formula is applicable. Now if you want, so there temperature that is equal to constant, so we know the formula ideal gas equation PV equal to mRT. So from here you can say that P equal to mRT by V. So what is the work done formula? W equal to integration PdV. So integration W, that is equal to integration, so what is the P? P is basically this mRT by V. So thus just put the value mRT by V into dV. From here you can calculate W, that is equal to mRT ln V2 by V1. From here you can say that mRT ln P1 by P2. From here is equal, you can say that PV ln P1 by P2. So this equation is applicable only when it is a closed system, reversible process, work crosses boundary. So both three is applicable, and there is ideal gas. Then this equation is applicable only for isothermal process. Okay, now for isothermal process you can see the temperature that is equal to constant, so P into V that is equal to constant. So from here you can say that P1 V1 that is equal to P2 V2. So V2 by V1 you can say that P1 by P2. So here in this equation MRT, so MRT ln V2 by V1, so you can say that MRT ln V2 by V1, you know that is equal to P1 by P2. So MRT ln P1 by P2. So this is the equation. This is very important equation. You have to remember this equation. So basically W equal to MRT ln V2 by V1, that is equal to MRT ln P1 by P2, that is equal to PV ln P1 by P2. Okay, so if you see on the graph, the volume is on the x-axis and pressure is on the y-axis. So here the process will be in this way or in this way. If the volume is increases, then there is a heat addition process, and if the volume is decreases, then this will be heat rejection process. So this is the heat rejection process. So this is the curve on, this is any process, this is a process for isothermal. Okay, now let's understand some law. First, what is Charles law? Charles law say that P equal to constant, V proportional to T. So from this equation you can say that V1 by V2 that is equal to T1 by T2. Now Gay-Lussac law, or you can say that Amonton's law or Dalton's law. Dalton say that if V equal to constant, P proportional to T. So from here P1 by P2 that is equal to T1 by T2. Now Avogadro's law say that if uh, uh, P and T if constant, then you can say that V proportional to N when P and T are constant. So here N is the number of moles. N is the number of moles. Remember these three formula. Now there is a adiabatic process. Adiabatic process means heat introduction is equal to 0. Q, the amount of Q, that is equal to 0. That means no heat transfer. So this is the adiabatic process. Adiabatic is same the the process in PV diagram will be same, like you can see that this is the P axis and this is the V axis. Here if the volume is increases, there is a adiabatic expansion process. You can say that this is the adiabatic expansion process, and if the volume is decreases and pressure is increases, this is the adiabatic compression process. Okay, adiabatic compression process. Now here the closed system work formula W equal to integration PdV. So this is applicable only when it is a closed system, reversible process, and work crosses boundary. Now, so for adiabatic process, we know the formula Pv to the power gamma, that is equal to constant. It is applicable only when it is a reversible process and ideal gas. Then you can apply this equation Pv to the power gamma, that is equal to constant. Here gamma is the adiabatic index. Now if you want to calculate the work done formula W equal to integration PdV. So Pv to the power gamma, that is equal to constant. From here you can say that P equal to C by V to the power gamma. So just put the value in this here, in this P. So C by V to the power gamma dV. So if you calculate this value, then you can get this formula W, that is equal to P1 V1 minus P2 V2 upon gamma minus 1. So this is very important formula. You have to remember this formula. W, that is equal to P1 V1 minus P2 V2 upon gamma minus 1. This is applicable only when it is a closed system, reversible process, work process boundary, ideal gas. If this four condition is there, then this equation will be applicable. Okay. Now P to the gamma, that is equal to constant. From here you can say that P1 V1 to the power gamma, that is equal to P2 V2 to the power gamma. Now one thing you have to remember, in this time later we have to proven this concept. So here a reversible adiabatic process is also known as isentropic process, because in the reversible adiabatic process there is no heat transfer is there. So this is basically isentropic process. The initial state isentropy, that is entropy, is equal to final state entropy. So here basically entropy is not change. Now another process, there is a polytropic process. Polytropic process say that polytropic process is that Pv to the power gamma equal to constant, n is the polytropic index, and n is basically minus infinity to plus infinity. Now in polytropic process, V is also transparent, W work done is also there and heat is also there. But in adiabatic process, heat is not there. Q is equal to 0. So in general, n is basically greater than 1 and less than gamma. Okay, basically the value of n is almost 1.2. Now if you want to calculate this work done, that is polytropic work done, the formula is P1 V1 minus P2 V2 upon n minus 1. This is applicable only when it is a closed system, reversible process, and work process boundary. So this is the work done formula. Now here there is a volume axis, this is the volume axis on x axis, and this is the pressure axis. So now this is the Pv to the power n equal to constant. Now if it is a adiabatic process, that means we know that Q, that is equal to constant, Q equal to 0. And if it is a isentropic process, when it is a isentropic process, when dq equal to 0 and it is a reversible process. That means reversible adiabatic process is also known as isentropic process. Okay, and if it is a p to the power gamma that is equal to constant, that means dq equal to 0 and it must be a reversible process, it must be a reversible process, and here we can apply the ideal gas equation. Now in polytropic process, p to the power gamma that is equal to constant in polytropic process, and polytropic process means heat is transfer and work is also transferred through the boundary. Okay, thank you, thank you. Please like, share and subscribe my YouTube channel. Thank you.